Hi everyone, today we're going to talk about designing the periodic table. So the periodic table is organized kind of like a calendar, very methodically. There's a reason for the way it looks. There's a reason for there's a big hole down here. There's a reason why down below there are like some kind of elements that are dangling down below and everything. So today what we want to do is kind of go over some of the basics of how the periodic table is set up and why it is that way. So first off, we have groups, right? If you notice, there are these stacks of blocks, right, for each one of them. And those stacks, they're all numbered, right? So they go from 1 all the way over to 18. The reason why each one of the elements is in that specific group is it's grouped together with elements that are similar to it, right? So all the elements in group number 1, for example, they're very similar to each other for the most part. And same thing with, say, group 11 or group 14 or group 18. They're all very, very similar. So each group has similar properties to one another, right? So for example, groups 12 to 14, they all have very low melting temperature. So if we go back 12 here to 14, these elements right in here, they're relatively easy to melt, right? So that's kind of why they've been all placed together for it. So they all have similar properties to one another. In fact, the whole periodic table is very similar to this. Elements that are close together tend to be very similar to each other for the most part. In fact, this screen right here, this is highly, highly important to you. You want to maybe even write this down or memorize this somehow. It's a very simple concept about the periodic table, but it's a very important one too, right? The two arrows that are on here, the two arrows are showing you more reactive areas, right? So the arrows are pointing towards where things are more reactive this way and towards things that are more reactive, going the other way on the periodic table. So in general, again, all of this is kind of a general speaking and everything, elements that tend to be towards the middle of the periodic table, they tend to be very non-reactive, right? So they don't react with other elements very well and everything. So for example, if you wanted to build something that explodes, right, you probably wouldn't want to use gold or silver or copper or mercury, or any of these ones towards the middle right here. They're just not known for being very reactive. It's not that they're not important. It's not that they don't have great things. Everyone would agree that, there's really good uses for gold and silver, for example, and everything, right? But exploding or causing big chemical reactions is not it. Now, in general, if you take elements that go this direction, right, the further down you go and the further to the left of the periodic table, well, the more and more reactive the elements get to. So especially once you get to, groups 2 and then group 1 over here, group 1, group 1 elements are ridiculously basically reactive. Some of them will explode just because they touch air and everything for it. So you got to be really, really careful with elements in especially group 1 and group 2. Same thing's true. The further to the right you go, the more reactive the elements tend to get. They get more and more reactive, especially once you get to, again, groups 16 right here and group 17 are super, super reactive, right? And we'll get to this later. Group 18 over here, right, is the one part of the periodic table that it's one of the areas where it doesn't follow this rule, right? So elements, there are two places where it doesn't follow this rule. All the elements in group 18 are basically super non-reactive. They're even way more non-reactive than the elements in the middle right here, right? So group 18, they're just super, super non-reactive. Think like, this is where you have neon, right? Helium, things like that. They're very, very non-reactive. The only other one that doesn't follow this pattern is little hydrogen way over here. Poor little hydrogen does not fit in very well anywhere on the periodic table. Hydrogen is also, it's basically it's one of the most reactive elements. It's super, super explosive and flammable and everything like that. So even though it's high up, because again, these would be super, super reactive, all the ones in group 1 are reactive, but the further up you go in general, they get a little bit less reactive until you finally get to hydrogen, though, it kind of bucks the trend. And same thing, these elements, very reactive, iodine and stuff like that, but not as reactive as bromine and chlorine, and then fluorine is very, very reactive, and so is oxygen up in here, right? So that's kind of a general pattern that the elements on the periodic table follow as far as their reactivity goes. So let's look at a couple of these, like fluorine, for example. I mentioned it's super reactive. It's also in your toothpaste, right? For it, fluorine, it's highly poisonous, but it's there trying to kill all those germs. How about this? Chlorine, helping to kill germs in your pool and hot tub. right? Same thing with bromine, right? Kills germs in pools and hot tubs. And even iodine, right? Iodine over here, it's often used on cuts and scratches and things like that. Or doctors will often use that to try to clean out, germs off of your body before or after operations. Again, I said in the middle, things like gold, silver, copper, very non-reactive. Over here on the other side of the periodic table, these elements, aside from hydrogen, which is gas, but all the rest of them are metals, and they're very soft metals. In fact, if you think about butter in different stages, different temperatures, right, that would be these metals right here. If you actually had a chunk of these metals, you could probably cut into them just with a knife. But they tend to be very, very explosive too. So you've got to be careful with elements in group number 1. And here's what I was saying. Group number 18 way over here, here's examples of them. They're the elements that we use for neon signs, even though, yes, there is an element neon. But when you see those pizza signs, let's say, for example, they don't always have neon in them, right? They have a combination of different gases, and that's how they get those different colors inside of there for it. These groups, while they are numbered, they also have names to them. So there are a couple of them, like group number 1 is known as the alkali metals. Group number 2 is known as the alkaline earth metals, right? Halogens are group 17. Group 18 are noble gases. The other ones are easier to know because the other ones, let's say groups 3 through 12, they're just all kind of grouped together, known as transition metals because they're so similar to each other. And then the other 4, they're easy to remember because group 13, 13, 14, 15, and 16, they're just named after whatever the first element is in those groups. So you have the boron family, carbon, nitrogen, and oxygen families. Those are pretty easy too. So really the only 4 that are kind of hard to remember, right, are alkali metals are group 1, alkaline earth metals 2, and then halogens and noble gases are 17 and 18. Right, the ones that are kind of like down here, right, they're called the inner transition metals, right, because transition metals are here. These are kind of connected to them. So they're known as the inner transition metals. Again, they're all so similar. That's why they're kind of like linked together for this. Let me show you a video. These are the elements over in group number 1. All right. So group number 1 is the one that's kind of famous because the elements tend to be so ridiculously reactive. So here's a picture of how reactive they actually are. Here's a short little video about it.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire, is burned with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
Well, you can see right there, you probably don't want any cesium laying around. your house, especially if it rains. There's one other short video I want to show you doing the same thing, but with larger amounts. People tend to like this video too, doing the same thing, talking about those metals in group number 1.
Whether you've left school or you're still at school, you can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! Wow, that is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. But still, there you go. Today's lesson:
Never mixed alkali metals with water.
I can't imagine why they wouldn't let them have any of francium. Now, this one they can't do because it's radioactive, so it's actually illegal to try to get some and explode it. Let's hear a couple last things that we need to get to, talking about the basics of the periodic table here. Now, we've been talking about the groups going up and down on the periodic table, but there's another way that you can basically classify all the elements on the periodic table, and that's going horizontal or left and right on the periodic table. Those are called periods. So they're kind of nicely shown here with colors. Like this would be, there are only 2 elements in period number 1, hydrogen over here and helium on this side. Then the next period are all of these elements that are colored orange, then yellow, and then green, and so forth, all the way down the periodic table here. Right now, these elements with their energy levels, it has to do with the electrons. Right? If you remember, you've got the nucleus at the center with the protons and the neutrons. That makes up the nucleus. But the electrons are kind of like spinning around in 3 dimensions, circling around that nucleus, and they're traveling at almost the speed of light. But we know that not all the electrons are the same. Some are just a little bit slower than the other ones, and some get faster and faster and faster, and that's what the energy levels are showing us. Right? So elements, let's say in group number or period number 1, right, a hydrogen and helium, that's showing you have those 2 electrons are spinning around it, right? But then what happens with the electrons is if a third electron tries to get into that first energy level, well, there's just not enough room. It's too small. It's too close to the nucleus right there. So what happens is it kind of gets kicked out and it makes a bigger second energy level, right? And so the same thing happens. Some more electrons can fit into the second energy level, a couple more because it's bigger. But then eventually what happens is they can't fit in anymore. So they get kicked out and they make a third, even bigger energy level, and so on and so forth, right? Then bigger and bigger and bigger energy levels come in. So each one of the elements that's that are in any one of these periods, it's another reason they're there. That's another reason why there's this hole right here, because there just wouldn't be enough room to fit other electrons into those different energy levels for it. Right. Oh, and here's kind of like a three-dimensional model that's trying to show you those different energy levels. Or here's another one where they can show you only 2 fit in the first shell, right? You can fit 8 into the next shell right here, and then so forth. Every shell you get to, they get bigger and bigger and bigger because there's more space. You can fit more electrons inside of those different energy levels. Right. Oh, and here's one. If I haven't talked about this yet in class for you, right? Here's the way the periodic table was meant to be. All those elements that are the basement elements down here, they really actually fit in way up here, and actually on the periodic table, that's where they actually fit in a little bit nicer and everything like that. It's just this way printing the periodic table would be way too big. It wouldn't fit in books and posters and stuff like very nicely. So that's why they kind of like chop it up and put it down below. So those elements are down below, right? These guys right here, right? There's 2 different, there are 2 different rows that are in there, and they both have names, right? They're both named for the first element that's on the far left of them. The first one is called the lanthanide series. Now, all of these elements that are in those basement in that basement group, they all are fairly rare elements. They're not ones that you and I interact with all the time, possibly with one exception. Because they're just more expensive for the most part and everything, right? So the lanthanides, they tend to be kind of these soft, malleable-ish metals. They tend to be kind of shiny, they're conductive and everything, but again, they're kind of expensive, so they're not usually used for things that you and I, oh, there we go, those guys right there. No laughing matter, get it? Laughing matter. Okay, anyway. They're not usually used for most things that you and I interact with, but with this one exception. Right, neodymium magnets. You might have those magnets, and they're very, very powerful. Right, those do get used, and neodymium is one of those elements that are down there. They're also used in like expensive cars, planes, trains, and things like that. Bulletproof glass, if you've ever seen it, same thing. That comes from the lanthanide series down there. So it's not that they don't get used; they're just not quite as commonly used as most of the other elements. I mean, most of us don't have bulletproof glass and everything. Then we're coming down to the very end here, right? Then comes this section right here, the actinide series. These are the same thing as the lanthanide series as far as they tend to be very expensive, very rare. These ones, though, are even more rare than the lanthanide series because these tend to be radioactive. So they're not things that you or I necessarily would want around us because we don't want to die terribly, right? But it's not that they don't have uses, right? So So for these guys, because they're radioactive, they're used for things like nuclear power plants, nuclear submarines, spaceships, and things like that. So it's not that they don't get used, but it's usually more government purposes for it. All right, hopefully this helped you with some of the basics of the periodic table. Make sure you take the quiz.